To start coding on quarters 2 Verilog, we first start with a blank document and we choose Verilog HDL file. Click OK. In this first exercise, we just want to fabricate a single gate, and we want to fabricate different gate each time. So we are not going to name this module to a specific gate name. Instead, we are going to call it just a gate. So we type module a gate. In this case, we are going to fabricate gates with two inputs. So we set the input port A and the other input port as B. This naming is up to you. You can call line 1 or line 2. Then the output, let us call F. Then we close the module name with a semicolon. And then we give some space. We match out the module with and module. Then we better save this module at this stage because we can quickly create a project. Then let us save this module. You can either click on the diskette icon here or you can press Ctrl S. It's better to always your work in desktop folder and then click a new folder so that we can organize our work in that folder. And in quarters 2, we have to use the file name.v, the same as the module name. And in that case, why not we also use the same name for the folder name. So in this case, I'm going to use a gate also for the folder name. And then you need to click open the folder. And for the verilog.v, we also use the name a gate. Better to follow the exact cases. Then after that, you will be prompt for a few options that you can choose in creating the project. At this stage, we will just select all the default value that's chosen for us in creating the project. So we will just click next until the end. Then finish. Then let's say we want to first create an AND gate, meaning you are going to assign to the output F the AND operation of A and B. We type in assign, we assign to F, F is the output with A and B. The single ampersand there is the operator for AND gate. Save it again, then compile. Okay, once finished, you can see that your total pin usage is 3 because you have 2 input and 1 output, total 3 pins, and the number of logic element that you utilize is only one AND gate. The next step is to see the RTL view of your fabrication. Under analysis and synthesis, look for netlist viewer and RTL viewer. So you should see an AND gate like this. most likely this means your code is correct. But we still need to simulate. To start simulating on quarters, we again need to create a blank file. Now the blank file is a VWF, which stands for Vector Waveform Definition, and this one is for university program that provided by Quarters. Click OK. Then you need to capture all the port that you have in your design. Right click, insert node or bus, node finder. Make sure you have pins all selected here. Then list. Then you need to see all the pins you have, which is A, B, and F. Then select all. Then click OK. OK again. Then you should see your input and output. We will be giving value to input. And then we need to see is the output is correct according to our expectation. So let's say we give a square wave to A, select A, and then in the timing diagram area, right click and give value of counting value. In this case, because A is 1 bit, we are only counting 0, 1, 0, 1, and 0, 1 at every 10 nanosecond. Just click OK. And then for B, we do the same counting, but now we extend to double the time period of counting so that we can have all four combination of values of A and B. We don't give value to F because F is the output. F is where we want to see whether or not our design is correct. Then we have to save the waveform definition. Then to run the simulation, we click the Run Functional Simulations from this icon. Alright, we have got our Nand Gate behavior. The output F is only high when both A and B are high. The rest will give F as low. So let us close this simulation result and let us go back to the code. Now this is an AND gate. Let us try OR gate. The operator for OR gate is the pipe character. This one. Change the single ampersand to single pipe. Then save it. Compile again. Let us look at the RTL view. Yes, we got our OR gate. Next, let us simulate with the same input waveform. So now we get the OR gate behavior, which is only giving a 0 to F when both A and B are 0. When either A or B or 1 or both, F will be 1. So in this case, we can try with other gates like exclusive OR, exclusive NOR, NAND, and NOR also. Let us do this quickly. This is exclusive OR. Then let us look at the RTL view. Yes, we get our exclusive OR gate simulation. we get our exclusive OR gate behavior. F is 1 when either A or B are 1 but not both. Next, let us change to Nand. We have to do A and B first, and we put this operation in bracket, and then we put a tilde to say that we want to invert the end of A and B to get the NAND operation. Then compile, finish, then let us look at the RTL viewer again. So in this case, the NAND gate that we get is actually a sequence of AND gate and an inverter. Simulate. We get the behavior of a NAND gate, which is only low when both input are high. Next is NOR. Finish compilation. Let us look at RTL viewer. Alright, it is a NOR gate. Simulation. Yes, we get the behavior of a NOR gate, which is only high when both input are low. Next is exclusive NOR. Done. Let us look at RTL viewer. So we get our exclusive NOR. Simulate. Yes, we get the opposite of exclusive OR, which is the output of F is high only when both input are the same, 1, 1 or 0, 0. Next, let us do the inverter gate. In this case, inverter is only having one input and of course only one output. This means we have to remove one of the input. Let's say we remove B, and the operation now is tilde A, meaning we invert A and then we assign to F. Save it, compile. So finish compilation. You can see now that we are only using 2 pins, 1 input, 1 output. Just now was 3 pins, 2 input, 1 output. And if we view our RTL viewer, we will get only the inverter. Then for simulation, obviously we need to recapture our IO pin because now B does not exist. So the best way is to remove all, but one by one, we delete this input, and the output, and then we recapture the entire input output again. So now we only have one input and one output. Select them all. Then we only give the input waveform to the input pin. Let us keep it counting at every 10 nanosecond. We have to save again because we have edited the waveform. Then simulate. So we get the behavior of an inverter, which is the inversion of the input. When input is high, the output is low. When input is low, the output is high.